Good afternoon, everyone. Welcome along to another in the GeoTalk series of geoeducation and outreach talks for the Geoid Special Interest Group of the Geoscience Society of New Zealand. Thank you so much for coming along today. I'm very excited to welcome John Tabor, who will be presenting to us today. John is a graduate of Swarthmore College. He did his PhD at the University of Washington, and he's the Director Emeritus of the Incorporated Research Institutions for Seismology, IRIS, now EarthScope, Education and Public Outreach Program, who's recently come back to New Zealand and now resides in Nelson. So we're very happy to have you back, John. So he retired from IRIS in 2022. But he started his career as a research seismologist at Lamont Doherty Geological Observatory and then was the EQC Fellow at Victoria University of Wellington, engaging in earthquakes hazard research. He's a past president of the New Zealand Geophysical Society, which is now, as we all know, amalgamated with the Geological Society to become the Geoscience Society, of who we belong to today. And he co-authored a book in 1996, Caught in the Crunch, Earthquakes and Volcanoes in New Zealand. He's received the AGU's Excellence in Earth and Space Science Education Award in 2023, and we're very excited to have John along today to tell us more about his education and outreach programs that he has been running in the United States throughout his career. So a little bit of housekeeping. Please put any questions you may have in the chat as we go. Any sort of short questions or clarification questions, John will answer during his presentation. But any kind of more discussion-orientated questions, we'll address those at the end. This session is being recorded, so just be aware of that. We'll make the recording available on our YouTube channel after the talk today. But yes, if you want to unmic or show your video, just be aware that they may end up in the recording as well. Kia ora. Thank you, everyone. Over to you, John.
Okay, well, why don't I see if I get the talk started. All right, good. Well, thanks, Jenny, for the introduction and for inviting me to give this Geo talk today. Jenny's been talking to me for a while now, trying to get me to give a talk, so glad to finally be doing that. I'm also really happy to be back in New Zealand after a rather longer than expected time in the U.S. While I was doing my EQC fellowship at Victoria, I got to do more education things and realized that education was really what I liked more than research. So I took the job over in IRIS and thought, well, I'll spend a few years there, learn some things, come back and do geoscience education here in New Zealand. Well, it turned out I stayed there till I retired, but at least glad to be back now. So today I want to do talk primarily about some seismology-related resources that grew out of the IRIS program and also the UNAVCO program and is now EarthScope. So what I really want to do is thank the teams, the IRIS EPO, the UNAVCO ECE, and the EarthScope engagement teams for all of the work they did in creating these resources, and especially Michael Hubenthal, who's really was instrumental in creating a number of the things that I'll be talking about today. And in case you're wondering, the picture in the corner is me with one of my favorite activities, which is using a model of 5 slinkies to show how seismic waves travel through the Earth. Okay, what I'd like to do is give a little overview of what EarthScope is, because I think people are here not all that familiar, particularly since all things have changed in the last few years. Talk a bit about why I think data use is very valuable for students, then go through some of the resources that use data access tools and some associated activities. Primarily, those will be at the intermediate secondary level, and then I'll also cover some undergraduate classroom and field modules and a couple undergraduate online courses that are available to students in New Zealand as well. So here's EarthScope. The EarthScope Consortium was formed, as I mentioned, out of IRIS and UNAVCO. IRIS is a seismology organization. UNAVCO was primarily geodesy. They worked in collaboration for years and then decided it made sense to finally merge together. I know people here in New Zealand are very familiar with mergers and changes, particularly the recent conversion of NIWA plus GNS into Earth Science New Zealand. Yes, I guess. So this was a smaller merge, but still took a lot of time. There are other names on this plot because there was also NSF decided to have the facilities that they were paying for through IRIS and UNAVCO to have their own names. So you'll see SAGE engage on things. And then there was an EarthScope project that went for about 15 years that was looking at the structure and evolution of the North American continent And since that was run by IRIS and UNAVCO, they felt that that was the best name to use going forward. So the consortium is 170 member organizations. They're US-based research and education institutions. And then there's about 250 affiliates around the world, mostly US, it's mostly non-US institutions. And for example, both Victoria and Otago are affiliates of EarthScope. So EarthScope is funded primarily through the National Science Foundation. And just to add yet another logo, another name, what they are funding is the new National Geophysical Facility. The funding just came through this month. And so now you'll probably over time start seeing that as the logo, the brand for all these resources. But what's being provided is really what IRIS and UNAVCO have been provided for almost 40 years. There's instrumentation, that's portable instrumentation, can be used around the world, but also global networks like the National Seismic Network or the Global Seismic Network and Network of the Americas, which is a GPS network. Data services provide all the data is available for anyone who wants to use it, and that's all being moved to the cloud. And then education, which is what I'll be talking about. The program itself is quite a broad program. I'll be focusing on just a small part of that today. Oh, sorry. So why have students use real data? You're probably all aware of this and think of this every day, but it's all about improving their engagement and strengthening their critical thinking skills. And since after all, real data is messy and complex, that's what students are going to see in future careers. It's good to have them start to understand that now as a student. And also, what I want to talk about is just learning about the students learn how that the data inform geophysical models that are used to understand the Earth system. So that's quite a range anywhere from whole Earth structure down to land use planning. So the EarthScope educational tools and the resources, as I mentioned, well, they're designed really for intermediate, secondary, and undergraduate level primarily. And one of the real advantages of being able to develop these tools has been very close associations, since it's the same organization with in the instrumentation group and also with data services. And one of my goals for this is maybe to see if there are some of the activities that could be even a better fit to some of the many New Zealand focused resources that are already in the GeoResources database. And thanks to Jenny for creating that GeoResources database. Very impressed with a number of things in there. And she's actually already entered almost all the things I'm going to be talking about in the database. The contributors just too many to mention in there, but there are, I mean, some of the ones that I think are closest to some of the things that we're doing are things like what Julian Thompson has put together, what AF8's put together, what GeoNet has. Then sort of final, the last bit of introduction is that since these are all educational activities, we have to look at the assessment. And because there's a lot of different kinds of things, activities, we try to use an assessment that fits the type and the scope of the resource. So things like animations are done pretty much internal review, classroom activities, we have teacher testing, and then evaluations after workshops. Software, we try to do piloting, usability testing, and then for the multi-week undergraduate modules that I'll be talking about, those have an external evaluator to run the assessment and also external faculty reviews. Okay, so now to start showing some of the tools. First one is just looking at a simple use of data is just global seismicity. So there are a number of browsers out there. I particularly like this one. It lets you you can explore really anything you'd like having to do with seismicity. It's got some 40 years of earthquake catalog in it. And we have an activity that can lead students to first looking at some area of interest, but then begin to dig into understanding plate tectonics. So you can then, of course, put the plate boundaries up to see where the plate boundaries actually are. And this exercise is really a global plate tectonics exercise because there certainly are a number of New Zealand focused plate tectonics exercises that maybe are better for New Zealand students, but I think sometimes it's good to also give students more of a global view.
I have a question, John.
Yeah.
Is that map movable so that we can see New Zealand is in the middle there, but if does it scroll from side to side or is it a static map?
No, it's a completely interactive map.
Oh,
I, I
cool.
I debated whether to try to jump into all these tools during the talk. Decided that was going to get too complicated going in and out. But yeah, this is completely interactive, like any Google map would be. And so, well, for example, then you can go zoom in here to New Zealand. So yeah, so you get to adjust the view you want. You can play with how many earthquakes you want to look at. You can say whether you want to have the newest earthquakes or the largest ones. You can adjust time range. You can adjust magnitude range, depth, and even data source. So you have a whole lot of variety, whole lot of choices on how you want to view your data. So you can really zoom into some particular area as desired. Now, the only downside I've realized with this is that this tool uses the U.S. Geological Survey catalog, and then you have the option of using the International Seismological Center catalog. So it's not the GeoNet catalog. So for local, some of the local sequences, like I was looking at Christchurch and also Kaikoura, the locations you get in this catalog are not as good as what GeoNet provides. So this is one of the things I'm going to be talking to the people who are working on this is whether it might be possible to add that catalog as another choice, because you'll see there's actually a data source choice already. It would just be a matter of adding one more choice. Then you'd have really the best locations for New Zealand. And then you'll see on this is showing depth by color, so you can clearly see the subduction zone. But of course, for students, that's not as simple to understand what that color means. So what you can do is you can uh, look at a pseudo 3D view. And now you're looking at a 3D view, and then you can rotate around and you can get a sense of the subduction zone from various different angles. And I'm just doing an automatic rotation here, but you can also actually pick up the cursor and you can adjust the view to be anywhere you'd like. So now I'm going to move on to say that's sort of the simplest, I'd say, seismicity data or seismic data to look at. Want to move on to some more other ways to use seismic data to look at the Earth. So this is a poster. Some of you may recognize this as a classic IRIS poster that was originally made 25 years ago. It's now online, interactive, and it allows you to link into a number of different concepts. So for example, when you can click into any of the text and it'll bring up the text in larger font. And in particular here that we're talking about seismic evidence revealing Earth's interior. So that's a big part of trying to use data is to get students to not just memorize, the layers of the Earth, but to say, what is the evidence for Earth structure? So to get to that evidence, you might say, well, how do seismic waves travel through the Earth? So if you wanted to do that, you can then it'll take you to a description, and then it'll take you to a interactive tool that lets you explore how waves are traveling through the Earth. And you can go off to the app from there to actually do that exploration. Now, if you go to the next step, then you might want to say, well, what's a shadow zone? You noticed you were learning some odd things were happening in that previous animation. What's a shadow zone? What does that mean? And this is really talking about the P wave shadow zone as you go around the Earth, as your seismic stations around the Earth are recording the waves that are coming from an earthquake. In particular, what you're going to be looking at is the waves that come here and just graze the outer core, and then when they hit here, they refract, they bend, and so you have what's called the P wave shadow zone, where the P wave no longer is the first arrival here, and so you'll see a delay in the signal coming in from here to there. So, but to then look at that, one thing you can do is you can start up. We have a series of animations that let you look at how waves travel through the Earth. So if you look at this, you'll start seeing all the different ways waves travel through the Earth, and also then you can learn about specifically about shadow zones here. So once you've done that, then you can say, well, okay, well, so where's all this data come from? And so that might lead you to, well, what's a seismic station? How is this data being recorded? And that takes you into a page where you have more animations just describing seismographs, and also an animation talking about what kinds of seismograms come out. What is what is a seismometer capable of recording? Not just earthquakes, but also helicopters landing, volcanic eruptions, and so forth. So if that gets you curious, you can then click here and say, okay, well, I want to find out, I'm actually going to look at a seismic station. What do I actually see for some recording station near me? So that takes you to the seismic monitor, or sorry, station monitor. Now, as I'm sure you're all aware, the GeoNet web recorder is very popular in New Zealand, so that New Zealanders can easily go look at what's happened on a 24-hour record at some station that's pretty near to them. The station monitor is designed a little differently in that, first of all, the EarthScope data center has data coming in from all over the world, thousands of stations from around the world. And so this map is showing all the different stations with the numbers, meaning how many stations are under each of these. So if you want to see what data or what sort of signal arrived at an earthquake, from an earthquake, sensing anywhere in the world, you can use this tool. But you can also zoom into New Zealand. It turns out not all the GeoNet, just some of the GeoNet stations are stored within the IRIS or the EarthScope database. So, but there are some, and so, for example, we can go to the South Karori station outside Wellington. See what that looks like. We get this plot. So this is a plot where there's minutes along the bottom. So this is 1 hour across the bottom for each line. And so this is showing 24 hours of data. Each line is 1 hour. And you can see here's a clear earthquake coming in. And normally it would default to going just to today's earthquake or today's activity, but you can also select from a choice of interesting earthquakes that have happened recently. So I've chosen this one as the 7.8 earthquake in Kamchatka that happened, I guess, a few months ago now. And if you decide, okay, tell me more, click me, you can do that. And that'll bring you up to some more detail. So if you're trying to understand a bit more about how seismic aids propagate what they tell you, this is now showing you the P wave, the S wave, and the surface waves coming in from that earthquake. You're looking at a total of about 40 minutes across the whole seismogram there, so that waves are taking that long to get from Kamchatka down to New Zealand. It shows you the path from Kamchatka down to New Zealand. And it also shows, if you want to, you can click on it and you can hear the first few seconds of the P wave arriving. If instead you want to look at a local earthquake, local New Zealand earthquake, here I've chosen a magnitude 4.1 earthquake that happened on the 2nd of October, a little bit south of Hamilton. And as before, you can come here, click on that earthquake to learn more, and it'll bring it up. And this time you'll see the P and S wave closer together. We're now looking at about 20 minutes total across here. And you can see the path again from Hamilton, or from the earthquake down to Wellington. And if you have more advanced students, then you can talk about, well, why are there no surface waves? And so this is a very deep earthquake. So really deep earthquakes really don't tend to generate surface waves. So it's a way to get some more discussion going about the data. Okay, back to our poster. Next thing is, perhaps now I want to get into what's, I think, a very important part of teaching about geoscience and a lot of other science fields is, what is a model? What is it? We're always using models while trying to get students to understand what a model is. So if you click on this page, you're just getting each of the top buttons just pops up an answer. So it's just getting students to be able to, to realize they have to interact to get answers to questions. And then you can also go into more, which will actually go into an online activity where they have to do more to understand what a model might be in terms of well, models in general, but in terms of science. But to actually jump to a modeling activity, so this is one that's designed for intermediate to secondary level, and with very simple assumptions. the students can actually make an estimate of the diameter of the outer core of the Earth. So I think this is quite amazing that you have students picking seismograms, global seismograms, and in the end, they actually have evidence that the Earth isn't homogeneous, and they can, within about 10%, they can estimate how big the outer core boundary, or what's the diameter of the outer core. So the way it works in this case is they make both theoretical measurements on a very simple Earth model, and then they compare that to real seismic data. So from that, they can then say, okay, something's happening, and they can determine the Earth must not be homogeneous, must be layered in some way, and they end up coming up with the diameter of the Earth's core. Now, you can do it. We have exercises both for teachers that prefer doing it with paper and protractor and ruler. You can do that in the classroom. Kids work in teams, and they have a team of theoreticians and a team of seismologists, and then teams have to combine their data, which also gives you a good sense of what it means to work in your own discipline team, and then working with another team that has a different skill. But you can also, you can do it as purely as an online activity, and it's got built-in assessments, so there are questions and answers along the way. And they get from that, they then can get a downloadable certificate, but also their responses are saved because some of the questions are open response, and that means the teacher gets a record of what the students have done. So if we were then to take this, here's the entry screen. We can let's select an earthquake. So let's select an earthquake. Let's select the Kaikoura earthquake as the seismograms we're going to look at. What that brings up is this is now what seismologists call a record section. So it starts from 0 degrees, which is right at the earthquake, to 180 degrees. So we're going around the Earth. We're measuring around how far around the Earth we are, where this is at the earthquake, and this is the antipode, the far side of the Earth. And the time is going along here. Total time is about 30 minutes on this. There's about 30 minutes of data shown on this slide. So what students have to do is they have to go and find the initial arrival. They pick all the P arrivals, and as they pick them, in fact, you can see here's the shadow zone picking up. It goes here, and then bang, you see where suddenly the arrivals have gotten later. So they make these picks, and the picks are saved for them, and so they end up with a plot. So this plot has got, again, distance from 0 to 180 degrees, and time and travel time in seconds, in this case, going up here. So we see now we have this plot pretty uniform, and then some jump, and you see that. So that's what the seismologists do with their collected data. Then the theoreticians have to say, okay, we're going to assume a simple homogeneous Earth. We're going to use a velocity of 11 kilometers a second, because you need a velocity because you need to know how fast the waves travel through the Earth. And then you say the earthquake happened here, and it then traveled from here to here, and it slowly it's traveling to each of these points along the way. And the students they decide where they want the data collected, and then the program automatically gives them a plot showing what's the travel time as they go from 0 to the far side of the Earth. So now we've got a theoretical curve, and we've already got our curve from the data. So combine them together, they don't look quite as neat and tidy now. With now the red is the observed and the blue is the model, but you still see this jump. So you ask students to sort of draw, it's not exactly a straight, not a true fit to the line, but just a general, because these are younger students, just a general connection of the points, and you see this jump. You ask them, where did that occur? In this case, it occurs at about 118 degrees around the Earth. So something's happening such that the signal gets delayed in the real Earth when you get to 118 degrees around the Earth. You then lead the students, and this is part of the online exercise, is they get continual questions. Whether, like in this case, do you have enough data to define the object. And if you give the wrong answer, then you get feedback to then choose the correct answer. But the idea is there must be something happening at 118 degrees from here to here. And so something inside this line is different than outside this line. So that's all you can have from one point. But since you can have earthquakes around the Earth, each one of those earthquakes can do the same thing. You have these lines coming out in those two directions. And so you start to see maybe that you can have a shape if you have enough earthquakes. And if you have a lot of earthquakes, now suddenly you find that you have a circle. So there must be an object in the Earth that's different from the homogeneous model. And you can then, once you've chosen, decide that's the case, you can actually measure how far that is. In this case, the measure amount was about 3,300 kilometers. And this estimate they come up with is usually within about 10% of the actual diameter of the outer core. So you think about the original discovery of the outer core would have taken, I don't know how long, sharing seismograms by boat around the world for months, months and years. And now a student does that in a matter of a couple minutes, and they can actually find the outer core. So now I want to, and what they really found is definitely not. They can now definitely say, well, yeah, the Earth can't be homogeneous, and so there is evidence for layers that they've been taught in class. Now I want to switch to a different sort of modeling. So this is now going to be looking at modeling of earthquake location. This is if you've ever worked with intermediate or high school students, maybe at the undergraduate level, the classic activity is to have students measure the P wave arrival time and the S wave arrival time and determine the difference in that time. And that difference allows them to figure out a distance from the earthquake to the seismic stations that they can then draw a circle on a map with that diameter. And that's often used on paper and often with just fake data. So it's nice. And so there's a one pulse for P, one pulse for S. So it's very easy for them to do. But it's not how earthquakes are located. Students end up really just trying to match to get their circles to cross. They don't really understand what's going on usually. So instead, we've been working on trying to use real data from real earthquakes and get students to explore how models are used to calculate locations. So it's how is it we have these big geophysical models, which then somehow are helping us to predict what will happen in the real world. So they're set up with step-to-step guided module. So there's a guided mode, so the students go step by step with information and questions. Again, with cues to questions. If they get the wrong answer, they get cued on how to find the right answer. And all these things also have an educator guide that goes along with it. And what we're trying to get, one of the things we want to do is get students to understand the importance of iterative models, that the iteration is something that's used quite a bit in science in general, and trying to get your model closer and closer to your data. So I'll show you two different approaches that we use. This first one, grid searching, is the one that we think really we'd like to see students get to, because it really should give them a chance to really understand, I think, really how earthquakes are located. So what they do is they have to pick seismic stations off a map, and then they have to pick the P arrivals, which is when the waves actually arrive. And they're given some background information on how to pick those arrivals, so they understand that. They then say, well, they then pick a grid about which they're going to say, okay, our earthquake is somewhere in this region. The one station with the dot is where the first signal came, so they get some sense of, okay, it must be in this region. So they have their stations around in this region. Then there's a velocity model built into the system, which the computer calculates just how long it would take in the model to go from every earthquake, from the earthquake to every station. And that compares the actuals to the predicted, and you get the root mean square error for the location. So This is where the students they do their picking online with the interactive tool. You move this bar around, and you can select your P-wave arrivals. That then all gets stored by the system. And then you come in and then you choose your grid area, and then the grid starts. And then the calculations begin. And what's happening is at every point, the computer is making the calculation of the difference between the model and the data, taking all the stations and the differences between arrival, predicted and modeled arrival. And it comes up and says, okay, this was the best, tells you the RMS error for that is that. So then students are said, okay, let's zoom in, which again is what a computer might do. Zoom in and make a more tightly spaced grid and run it through again. Of course, the computer can do this much faster, but we slow it down so the students can see what's happening. And now this RMS error has gone down because these colors are relative RMS errors. Zoom in again, and you'll see now that once you do this, now the RMS error is, once you get to the best station, now it's gone down quite a bit. So this shows that you can fairly quickly, with just nothing, as long as you have a model of how you think waves are traveling, how fast waves are traveling through the Earth, you can fairly quickly come up with a location of your earthquake with nothing more than just the P arrivals. And yeah, and so once you've done that, this is being done originally for a fixed depth, usually 20 kilometers. Then you can say, okay, well, how about depth? And so it'll automatically run through and tell you this is depth and this is RMS error. So error is increasing this way. So in this case, it says, oh, well, the RMS error depth, well, the RMS error starts going up pretty rapidly once you go beyond about 20 or 30, well, about 30 kilometers. So you can find that in this case, the depth maybe is, I think the best depth was about 23 kilometers. So you get not just the epicenter, but also the depth. So it means you can, in New Zealand, this can work to, or well, actually it doesn't, there aren't as many stations in New Zealand, but globally, you can have students look at subduction zones and locate earthquakes that are up to 600 kilometers deep with this very simple system. And then, of course, you can then check your work. And so you get a certificate. And as I mentioned, then when you do that, then along with the certificate, it sends a note to the teacher, who then is able to assess how well you've done with your work, with your location. Now, then the next step is to go to what really is done even more often with current location techniques, earthquake location techniques, and it's a more advanced system because the students are really assumed to understand vectors. So we think this will work maybe best for advanced secondary students and also at the undergraduate level. This is still coming soon. The software and the activities are all in place, but right now we're still doing user testing, so still tweaking a bit. So you won't see this yet available actually online. But what this does is it's calculating the root mean square error, same way as a grid search does at each location. But the difference is it gives information about the difference between the actual and the model arrival times for each of the stations. So the students start to get a greater understanding of what does this error mean? What the error means is what's happening individually for each of the stations. So in this, the length of the red line is going to be it's giving you a sense of the model versus data arrival time. So what's the error at each station? And so each line is one station. It's pointing either to or away from the station. And then the green line is the vector sum. So that's why the students really need to have some sense of what vectors are. In this case, there were 8 stations that were selected from the map, and then the P arrivals were picked. And then I've already zoomed in a bit, so you really only see a few stations. You see the closest stations here, down here, and there's one over here somewhere. You can see, and over there. So a few of the stations are still on the map, but the idea is that it always starts at the station that had the earliest P wave arrival time. So right now you can't quite see all 8 of the red lines, but you will as you start to move around. And the thing to do is also watch this RMS error. So this is the original RMS error, just assuming that it starts at the station. So now what you do is the green arrow is saying, okay, that's the direction you want to go to reduce the error. And once you've done that, you can very quickly zoom in a couple times, in fact, and start to see, well, first of all, you see this RMS error has already gone way down. And then you can move it down even further. Again, the error, because you're looking at the sum of the errors, you can figure out which direction you need to move to reduce the difference in the travel times between the model and the data. Now, in this case, you've really got a pretty good RMS error, but one station is completely out. So you can then actually click on this and you can come up and say, well, did I make a mistake with my pick? So this is showing two things. It's showing the pick you make, the red, and then what the model said was the arrival time. So in this case, they say, oh, well, my pick is good. And so this is also an important thing for students to realize that the data, back in just a second, it's important for students to understand that the model is in this case, a uniform model, but for some reason, the waves are traveling more quickly from the earthquake to that station. But you shouldn't change your pick because that's the true data. So you can still, so you say, okay, I'm going to leave that. That is probably correct, but now I can get even closer into the actual solution. So now the RMS error has gone down even further. No, there's that. So first of all, it lets the user get a much faster solution. And that's what's happening in the computer. In the case of the computer algorithm, it's doing the same thing. It's always calculating how the error is changing from a particular position, and so it always is moving the location in that direction. It gives students additional exposure to really how you determine best fit between a computer model and the real world. And it's also then a lot closer to how earthquakes actually are located compared to the S minus P circles approach, which has been used for so long. And so our hope is that people will see that this good search and for most students and the residual approach could actually lead students to understand a lot more about how earthquakes are located. And to learn about models. But again, really it's about learning about models, as they'll continue to have to deal with models versus data in a lot of different fields. So what I've been showing you so far are all available through a searchable database of resources. I've shown, this is the page here. In this case, I've selected lessons and I've selected novice lessons. You can also select concepts. And you'll see, like, for example, in this case, there are 32 lessons that are at the novice level within the EarthScope database. And you'll notice that this SAGE is here, EarthScope is here. So not to worry that the database has stayed the same. It's just essentially just the branding has changed. But through Jenny's wonderful efforts, this link is already in the Geo Resources database, so you can get there that way, or I've put it down here at the bottom. So most of what I've shown so far is really best at the the intermediate and secondary level. And there's some of the tools, like the last one, is you could use at undergraduate level as well, particularly if you're doing the explore mode and not doing the step-by-step guided mode. But now what I want to do is switch to some undergraduate multi-level modules that I think really could be used here in New Zealand. And also a couple courses. So this is a set of resources with the name GETSI Geophysics Tools for Societal Issues. And it's a curriculum. A curriculum is designed to have students sort of learn how to tackle real-world challenges, looking at natural hazards, environmental management, urban planning, climate change. You'll see that urban issues show up a number of times because one of the goals for this particular set of modules was to engage students where they are. So that engage students who may live in a city environment and don't think of geophysics as something they would ever want to do, but to show that geophysics is actually, it can be used in urban and near urban environments as much as being out in the sort of field geophysics that a lot of us we're used to doing for geophysics. Started off, it was purely a UNAVCO geodesy project, and then it expanded into seismology as well. These, because they're larger modules, they've been well tested, and they're designed typically to be a 1 to 3 week course, or 1 to 3 week module, and they're done both for at introductory levels and majors level. So here's an example of the modules. So this, at the introductory level, they're all primarily geodesy related. So you can just generally measuring Earth with GPS, so understanding plate motions, some surface process hazards that you can address with GPS, looking at sea level changes with GPS, looking at hydrosphere. Again, GPS can be used for that, and then monitoring volcanic activity, and then looking at the risk, and again using geodesy. Then at the majors level, there are things you can use INSAR, so measuring necessarily imaging active tectonics. Again, looking at water resources, just looking at the strain happening around earthquakes, modeling flood hazards, looking at landslides, and also and you can actually glean some things from relative to climate, particularly with melting of glaciers. Then the field modules are both both geodesy and seismology. So there's you can get kinematic GPS, looking at high resolution topography, and looking at gravity magnetics, looking at resistivity. So it's near surface geophysics. And then two that I'll talk about are looking at seismic refraction, which is used in a lot of undergraduate courses, and also looking at ground penetrating radar. So for the looking at the seismic refraction, it gives you an example of how all these modules are designed. In this case, uses real seismic data. It's showing how the seismic methods are used to address real world problems. And then the key is that everything for the module is included. So you've got PowerPoints, videos, activities, assessments, and it's designed to be flexible. So you can just pull out an individual activity, or maybe just one part of the module. You can use the exercises as homework, or you can do them as in-class assignments. And then the idea is that these can be extended to collecting local data. But they all have data. These are all designed with data included. So for example, in seismic refraction, a lot of the data use is done through Excel spreadsheets. So students are doing their calculations that way. But this just shows an example for the three, and here shows that it's considered a sort of intermediate level course, and it's a 3 week. It's figured you can do it 1 to 3 weeks with sort of 3 units. So typically, if you use the whole thing, it might take you 3 weeks. But it shows all the structural materials. It then shows, and then it has the introducing shallow seismology, how waves travel, and then it has a case study. And pretty much all the modules do the same thing. There's a case study, which is where the actual data comes in, and then they all have assessments. And they almost all have an instructor story, which is some other instructor who didn't create the course, shows how they used it in their class. So then for GPR, ground penetrating radar, again, it's got the same sort of flexibility. And this is explaining the physics of GPR, showing how you can locate, in this case, how you can use GPR to locate underground things which are not necessarily out in the field, but are right in, it might be right in the town. Excuse me. Looking for buried pipes, and also it's used a lot to locate graves. And so and the students have to sort of learn about the capabilities and limitations of GPR. And same thing, you get the whole table of contents. Whoops, I hit that. and instructor stories. So and then if you want to try to extend it to collecting your own data, then there are videos that are available. So they've created videos on, for example, how to do seismic refraction, how to use a ground penetrating radar, and then also how to do electrical resistivity survey. So it works particularly well if you have the same kind of equipment. In the US, this was designed so that institutions could actually borrow equipment from EarthScope. And so these videos are exactly the same equipment, but similar equipment is used here in New Zealand. So a lot of universities will have some sort of seismic refraction equipment or any of these sorts of equipment, and so the setups would be very similar, I think. Okay, so now I'm going to move from the modules for faculty to this is now students taking part in workshops. So the seismology skill building workshop is MOOC style, so that's the massive open online course. So it's a 12-week computing course. It was originally designed to take a place of internships that all got canceled in the first year of the pandemic. And it's focused on undergraduates, but there's been so much interest that now they accept grad students as well. It's grown from 900 students the first year to 2,300 students this year from over 60 countries. And there have been I think this last year, there were about a dozen students from New Zealand took part. So it's really all about, since there's no, at least in the US, there's no standard place for students to develop scientific computing skills. So this is trying to develop those scientific computing skills, but using the seismology content knowledge as the sort of at the base, what ties everything together. So it's asynchronous. I say it's about 6 hours a week per. They're expecting about 6 hours a week of work per course. There's no cost. It doesn't require there aren't any prerequisites. But it helps to have at least some math and some physics. And here's some of the topics that get covered. So you may be familiar with some or all of these, but particularly it's trying to use things like well, web services, Jupyter notebooks are a big part of it, Linux, MATLAB. And the way it works is there's the learning management system provides real-time feedback, just like with the other earlier things I mentioned with the intermediate and secondary school students. There's feedback as you answer questions, you get feedback. But then a big part of these courses has also been a Slack discussion that ends up peers help each other. So it's obviously too big a course for the faculty to be directly interacting with students, though they can answer questions if need be, but primarily students help each other. And that has worked very well. And they get very good, the responses are very good. Like nearly 70% reported they learned a lot. And they really, and again, 75% had said great growth in computing skills. So most of them are geoscience majors, but about a third are not. And so that runs once a year over the US summer. So it'll run again next summer. Then one last course, something called I don't know if any of you have used this, but it's a group of tools called the generic mapping tools. It's used heavily in some areas of geophysics for making all sorts of publication quality maps or just presenting data. And so this one is another online course, also purely asynchronous. It ran this last September, so it will probably run again a year from now, but would again be open to anyone from anywhere. And that's a course that they expect students to spend about 30 hours over the course of the whole course. And some of the topics, so if students want to learn more about Unix and then GMT and accessing data, and along the way learn more seismology and geodesy. And then the goal is you can have be able to create high quality figures. And these are it's done with automatic grading. So again, there's no direct interaction with the faculty, but the automatic grading helps the learners to understand what, where they stand in understanding the content, and how they get credit by having worked all the way through it. So that's the tour. And so just to give you a very brief summary, uh, what I've tried to go through is the first set of tools were sort of exploration tools, looking at seismicity, looking at seismic waves, looking at seismic stations. So it's sort of some of it is curiosity driven, but they all have active, student or actual activities that can be used with those tools. And then several things I talked about the geophysical models, both using the layered earth activity and earthquake location. And then the undergraduate classroom field modules, I talked about seismic refraction and ground penetrating radar, but there's that whole series of modules that are available. And then mentioned these two undergraduate courses, the skill building workshop and then the generic mapping tools. So with that, I just thank you very much for your attention. Hope you found something that might be of potential use or at least of interest. And I'm happy to take questions.
Thank you so much, John. That was excellent. Certainly a lot of material there
Yeah,
for people to use. I'll open the floor, hand the floor over to anyone who has a question. Ilmaz has put in the chat, thank you for bringing those resources alive. While you've been speaking, I've added 2 more of them to the GeoResources database that I realized I'd missed.
yeah,
So thank you for that, John. But yeah, does anyone online have a question? Feel free to pop your question in the chat or just raise your hand, unmute yourself. For a question for John, we've got a couple of minutes left in this session. Mila.
Hi, John. Yes, hi. John, we met in GSNZ last year. I don't know if you remember, but
yeah,
yeah. Thank you so much for the overview. So I don't have a question, but it is really good you did this because, the IRIS resources are so many, and sometimes you kind of get lost,
yeah,
going through the many pages. So these were really good. I actually used, you should be happy to hear the interactive earthquake, the first one you mentioned.
yeah.
And I used on a first year course, so we have about 300 students that get exposed to that. So, and they work really well with that. So they're all from different backgrounds, so it's perfect. But I loved your layered earth. And Jenny might know, we were at a meeting a few weeks ago. And what is good about that one is we're meeting with teachers, earth and planetary science teachers. Yeah. And we kind of mentioned that, one of the skills students need to get is a bit more quantitative. And of course, they're always really scared of, well, what do we teach and how much do we teach? Some are more comfortable than other teachers. And I thought that tool helps them. So I'll probably go when we have another meeting with the teachers. We'll have one in Auckland. I'll probably showcase that one because it would fit the New Zealand curriculum for Earth and planetary science really well.
Yeah,
So,
that really is it's a fun activity. If the teachers are willing to do it with paper and pencil and protractors, then in some ways
yeah.
it's more tactile and the students get a lot out of it. But that takes some setup time. So that's why we
Yeah.
have creating the online version, which the teacher can then be walking around the room answering questions. So both ways work. It just depends on the teacher and the amount of time they have to set up. But if you use the online version, there's not much setup except maybe some discussion beforehand.
Yeah, maybe they can combine, but yeah, I didn't know about it and I really loved it. So really I wanted to say thank you, and that hopefully we'll be at least using our outreach activities too. So yeah, that was really great. Yeah.
Kia ora, thanks, Mila. And thank you, John. Any other questions or comments from the floor before we wrap up today? Yeah, I agree with what Mila said. I think some of the teachers that we met at that meeting would be very interested in sharing these resources. So I think we might even make just a short list, because there is a lot, but maybe a short list of like the really kind of basic ones, the easiest ones to use as an introductory step for them, and maybe share that with that group. That would be really great.
Yeah, because that's something I haven't. I mean, I sort of looked at the New Zealand curriculum a bit to try to get a sense of where things might fit. But that's where I'd be happy to work with someone to figure out what are the gaps right now that you see, that could be filled in by something, and maybe I could say, oh yeah, here's an activity that's close. Maybe it only needs a bit of modification, because all these things are, since they're all paid for by NSF, it's all free to use and free to modify to whatever fits the local teacher needs.
Amazing. We will definitely follow up on that. Thank you so much, John. For now, we're out of time, but yeah, thank you all for coming along today. And thank you, John, for sharing the EarthScope Consortium resources with us. I think, yeah, there's definitely a lot of potential, and we'll definitely be in touch.
Okay,
So
great.
kia ora. Thanks a lot, everyone. Enjoy the rest of your day,
Thanks,
and
Jenny.
I will make the recording available on YouTube at a later date. Take
Okay.
care,
Thank you.
everyone.
Thank you all. Thank you. Bye.
Kia pai tō rā.